It's my great pleasure to have, and our great pleasure to have Irit Dinur here from Weizmann Institute here. We had a great year, or a great half a year, and maybe not so great half a year at IAS in between. The pandemic started, but overall it was still a very nice experience. I have great memories of this. So yeah, it's a pleasure to hear Irit on. She'll talk on locally testable codes, recent work. Thanks, Irit, for agreeing to talk.
Okay, thank you. My pleasure, and thanks for the invitation. We don't travel, at least we do these seminars. That's kind of cool. So, hi everyone. I've given this talk already a number of times, and I have a keynote presentation, and I can just kind of go through it, but I don't know you so well, except for Andre. So I don't know what you know, what you care about, what's not interesting for you, what's interesting maybe. And I'm hoping maybe we can make it a bit more interactive so that it's maybe more useful. Because there's videos of me talking about this already online, so you can just go and watch that. But you made the effort to come here, so maybe don't be shy to ask questions, and okay. I mean, it would be much easier if we were in person, but since we're not, then let's kind of try to do it. We'll see. All right, so I'm talking about something that's called the locally testable code. It's an error correcting code with an extra property, and this is based on joint work with friends of mine. All of them are mathematicians. Shai Evra, he was a postdoc at IAS when Andre and I were there together. He's now a young assistant professor here at the Hebrew University. And Ron Livne is a professor at the Hebrew University. Alex Lubotsky, he was back then at the Hebrew University, now he moved to Weizmann, and Shachar Moses also at the Hebrew University. Okay, so anyway, I'm going to talk about error correcting codes. Forgive me for these not beautiful circles. In error correcting code, I kind of assume people know what it is, but I prepared these slides also for kind of a broader student kind of audience. So I have a slide about it. I'll go through it. It's one way to think of an error correcting code is just it's a linear subspace. It's just a vector space, and we think of the field with two elements, so 0, 1 to the n. And every element in the subspace, a point, or you think of it as a string with n bits, is supposed to be a code word that encodes some kind of message. So really an error correcting code is like a dictionary that says, if you want to tell me this word, you should send this string. If you want to tell me this word, you should send that string, and so on. And why do we need this dictionary? I mean, we could just use natural language. The reason is that we want to transmit the information in a world where there's some kind of errors and noise that can happen. And so if I transmit two words in natural language, like in English, that differ only on one letter, they might be confused with each other. And instead, we use an error correcting code to make sure that all the different words in our dictionary, in our code, are far from each other. So the strings are the code words. Okay. So we're imagining a situation where I'm sending to you some string of bits. Maybe I'm sending out some kind of a shuttle into space, and then it's going to send to me some data over many, many years, and noise will happen, cosmic rays, whatever. So I want to be able to recover the data and erase the noise. And the way we do it is that if we arrange a code that has code words that are far apart, assuming not too much noise happened, we can do it. This is a very famous paradigm of dating back to the 1940s and early 50s by Shannon and Hamming. So we measure the distance between two strings with the Hamming distance. It's just counting how many indices, the distance between x and y just counts how many indices x differs from y, and we normalize by n, so we can always talk about parameters between 0 and 1. And we want two things. We want the code words to be as far apart from each other. That will allow us to correct as much noise as possible. And on the other hand, we want to have as many code words as possible in our code so that I don't need to spend so many bits to tell you what I want, but rather the number of bits I spend is similar to the number of information bits. If you look at this picture here on the right and top right, this is a geometric picture of the code. Every point here is supposed to be a string in this linear subspace C, and the little circles are supposed to be geometrically depicting all the strings that are of Hamming distance kind of close to the code. So it's like a geometric ball that says all the points inside this circle are kind of close to this point. Okay, and the way we do, we arrange generic correcting code is that we arrange it so that there's a big ball around every point that's kind of disjoint from all the other balls, so that if you start with some code word here. By the way, you can see the arrow of my mouse?
Yeah, it's good.
Good. Okay, so you start with some point here, and then some noise happens, so it's like you're traveling a little bit far away. As long as you don't completely exit the ball to another ball, there's a unique way to decode. I just look at the received word is some point that's here. It's not necessarily in my subspace, and I just go back and find the closest red point to my received word. Now, this is more simple than it sounds simpler than it really is, because how would you actually implement this? This is non-trivial at all. This ball consists of an exponential number of strings, and you can just search over all the strings until you find the code word. That's fine, but that's not very efficient. And it's a challenge to do it in an efficient way. For example, if the code is a linear subspace, it's not as if you can invert the matrix, apply it to the noisy code word and expect something to come out, because when you multiply some vector with a matrix, you get something. Now you add some noise and you invert, who knows where you will get. So this is the problem of decoding, and it's very, very well studied. Okay, so there's two kind of interesting parameters for code. One is the distance. It's going to allow us to correct as many errors. The bigger the distance, the more errors. And the other thing is the rate, which tells us how many code words we're managing to squeeze into our linear subspace. And we want both of these to be large. Kind of a golden standard of coding theory is to have both of these parameters when I normalize dividing by the block length n and the size of the strings, they need to be bounded away from 0. And we think of kind of n as going to infinity. All right, so this is error correcting code, and you probably have seen these things. It's very basic and super useful. Now, local testability is a more recent kind of thing to study. It's maybe started in the 1990s, so maybe 50 years after coding theory was begun. And local testability is talking about this. If you give me some string W, so it's not necessarily in the code, it's over here, and I want to know if W is in the code or it's not in the code. How do I do it? So local testability allows me to decide such a question without even looking at the entire string. So super, super efficiently, you just look at a small random part of the string W, and you can decide if it's in the code or not. That's local testability, and it's part of a more general framework of property testing, where you're given some big object, like a string in a code, but maybe something else, and you want to probe it kind of randomly and just look at a little part of it and deduce some property of it. You won't deduce it with 100% certainty, but you will be able to make some kind of assertions about it. So here's how we define local testability. A code is called locally testable with Q queries. This refers to how many points in the string I'm going to read, how many bits, Q. If there is a tester T that has query access to the given word W, it reads Q bits in W, and then it says, okay, it's in the code, or it says, no, it's not in the code. So this tester, you should think of it as kind of a distribution over the bits of the code word. It's randomized, and it just decides to read these q bits, and based on this, it will output its answer. And the properties that it satisfies are these. If the word is in the code, it will always say yes. But if the string is not in the code, then well, I would love to say it will always say no. Then it would be perfect, right? But that's impossible. Why is it impossible? If you had a word in the code and someone came and just changed one bit, it's already not in the code. But my tester is only going to read a small tiny part, so there's no way it can catch that one bit. So I cannot expect this from my tester. What I can expect is that if someone changed the word in some alpha fraction of the bits, then the probability that I will say, that the tester will say no, is proportional to this alpha. So that's what's written here, that the probability to say no, to reject, is proportional, there's some constant here, to the distance of the word from the code. How many bits you really need to change W to make it in the code. Okay, so that's a definition. Q, the number of bits your tester is reading, is the locality. And these are called LTCs, for locally testable codes. Now, just to tell you, this is kind of maybe a weird property. If you've never kind of heard about property testing or probabilistically checkable proofs, it would be a very weird thing for you to look at. Shannon and Hamming would not have thought about it because for one, a random linear subspace, maybe I could have said earlier, a random linear subspace is a good code in the sense of having good distance and having good rate. You take a random linear subspace of dimension of your choosing, and you can prove that it actually has good distance. But it will definitely not have this property. And so you won't even imagine that codes like this should exist. And the only reason we know that they exist is because of all this literature about probabilistically checkable proofs and so on that show that such things can happen. That, you know, for example, any problem in NP like 3SAT has a verifier that doesn't even need to read the entire NP witness in order to decide if it's satisfiable or not. It can read only a tiny part. That's the PCP theorem. That's also kind of a local testing in spirit. It says you don't need to test the entire NP witness. You only need to randomly look at a tiny part of it, and you can decide. That's what the PCP theorem says. And this is where this notion and these objects originally came from.
And how can we check that something is not locable testable? For example, how do one can prove that random code is not locally testable?
Is not. Oh, that's a fantastic question. Okay. Why did I say a random code is not locally testable? How do you know that it's not locally testable? So I'll give a more detailed example later, but just to say now, suppose I can show you in a code a word that is very far from the code, so it's far from all the elements in your subspace, but it satisfies almost all of the parity checks that define the code. There's only one parity check that it doesn't satisfy. Then at least you know that a parity check is just a linear constraint that defines the code. So if it satisfies almost all the parity checks except for one, then at least you know that the maybe naive tester fails. The naive tester would be, how am I going to check if my word is in the code? I'll take one random parity check and apply it to my code word and see. Okay, maybe this answer is not quite good. Let's come back to this question later when we talk about the expander codes. Then it will be more clear.
Irit, can I ask a quick question also?
Please.
So can you get any kind of error correction from here, or you'll talk about that also?
You're asking, suppose you have a locally testable code, does it also mean that it's you have an algorithm for decoding it? Generally, when you think about these objects, you expect them to also have a decoding algorithm. I don't know of a theorem that says every locally testable code can be decoded in polynomial time. I don't know that, but But the codes I'm going to talk about will be able to be decoded, because kind of when you prove local testability, your proof is kind of showing you how to find the code word. So it's kind of an algorithmic proof,
Okay.
but it's not inherent.
Okay.
Okay.
Thanks.
Thanks for the questions. Any other questions or anything, please feel free. Okay, but I'll get back to the other question soon. Now, let me just tell you another way to think about local testability. So you have a linear subspace C, and it's defined by some linear constraints, T1 to Tm. Okay, so it's the subspace of all strings that are, say, orthogonal, that have inner product 0 with these bunch of test vectors. Then there's two ways you can measure distance from C. One is the natural way, the Hamming distance. You want to say, when you're given a string, how far is it from C? It's just how many bits you need to flip to make it in C, the smallest number of bits you need to flip. That's the Hamming distance. And the second distance is kind of ad hoc. I'm just defining it for the sake of the lecture. Let's call it the testing distance, or the T distance. I'm going to ask how many of the linear constraints are unhappy, are unsatisfied by the specific W that we are given. If W is in the code, by definition, all the tests are happy. If W is not in the code, some number of the tests are unhappy, maybe 0, maybe M, maybe something in between. And I can define this to be some kind of measure. Now, this measure is not independent of the tests. I can take a linear combination of these tests, get some other T primes, and the measure will be very different. But per a specific choice.
So here they're independent. Sorry, they're independent. This test.
The T1 to Tm don't have to be independent. I can repeat. I can also have T1 plus T2. I'm not saying
not necessarily all the tests possible either. So it's
right.
just some set.
Exactly. The number of possible tests. If these were all independent, then all possible linear combinations of them would be all the possible tests. So I'm not talking about all of them, just some specific set of tests.
Okay.
Okay. And I'm also thinking of, okay, I forgot to add it here in the word test. I maybe should have written local tests, because think about kind of the case that we really care about is when the TIs, each one of them is actually a very low support vector. It only looks at a few bits. So say T1 is just 3 ones somewhere and zeros everywhere else. So to check if a word satisfies T1, I only need to read 3 bits in the word. Okay, so this is what I have in mind. The TIs are very sparse vectors, local tests. Okay, so what can we say about these two distances? The Hamming distance, it's natural, but it might be hard to compute. If you give me a W and you give me a description of a subspace, it's not clear how to figure out what's the distance of W to this subspace. I can go over, as we said, the entire ball of changes to W until I reach something in the code, but that's inefficient. Whereas the T distance is very easy to compute, right? Either I just go over all the tests and check each one, or I can just randomly choose a few of them and check them. So that's actually super easy to compute, even in constant time, if I'm willing to get some kind of estimation error. So an alternative definition for a locally testable code is these are codes that where the T distance is a good estimate for the Hamming distance. Okay, these are codes where if you are far from the code, then you know that your T distance will also be large. Okay, and also vice versa, but that's easier to do. So you see, if these were say independent tests, it should be clear that there is a word that satisfies all of them except for one, and that would be not a good. So then this specific set of tests is not a good tester. Okay. Okay, so that's again just understanding what an LTC is.
But here we additionally required that the tests are linear, which is not generally is not required.
That's absolutely true. So there's a whole literature about this, and it can be proven that for a linear subspace, if you come up, very sophisticated test that's not linear, there must also be a linear test, right? I mean, the test could also compute some other function of the bits. It doesn't have to compute some modulo 2, but it turns out that this is true.
And
Okay.
is it an easy result? Or is it a hard result? This one.
I don't remember. I don't think it's super hard. I don't remember exactly. Maybe you look at the function that you're computing, you look at its Fourier decomposition, there must be some Fourier character that has some weight that's correlated with the function. I don't remember.
Mm-hmm.
Okay. Okay, so why do we care about locally testable codes? Well, one thing, notice it could be potentially useful. Suppose you're using a code for transmitting information, and once the information passed, maybe some noise happened. You want to know if a lot of noise happened or not, but you're not going to devote all this algorithmic effort for decoding. So instead, you just probe it in a few locations, check whether errors happened or not. If too many errors happen, you just say, okay, I'll throw this away. I'm just asking for this code word again, if you imagine some kind of interactive situation. So LTCs could be useful in practice. I don't rule it out. Okay, so let me tell you some historical context, and then we'll get to a construction of a locally testable code. So as I mentioned, these objects were studied implicitly when people studied probabilistically checkable proofs in the late 90s or early 90s, actually. First, they were not kind of defined explicitly, but they were lying around there. And a decade later, a more systematic study was initiated in a paper by Goldreich and Sudan. And they asked this question of, for codes, we know that you can get constant rate and distance. What's the best rate you can get for a locally testable code? And then there were a sequence of works essentially imitating or using the technology that was already there for PCPs to get locally testable code with similar parameters. And we could achieve something like rate that's going to 0 as the block length grows, but only in inverse polylogarithmically. So rate that's kind of okay, but not constant, which is, like the golden standard of coding theory. And so this question emerged, are there these C3 locally testable codes that have both constant rate and constant distance, and also testable with constant locality, meaning the tester only reads a constant number of bits out of the entire n-bit code word. And at that point, experts maybe doubted the existence. Some people said that they can't exist. Even we tried sometimes to prove lower bounds. Okay, but the kind of opinion went back and forth about this. Okay, a few years later, these objects kind of made their way into TCS called the high-dimensional expansion. High-dimensional expanders, okay, so they're things that some people knew about a long time ago, but in my sphere, kind of we heard about them a few years ago, and they're very interesting combinatorial objects that have these local to global features. I might talk about them later, but they kind of gave some kind of hope for getting such LTCs. Okay, and so this is the main result of this work. It says that for every rate, so the rate is how many code words you fit. For every rate between 0 and 1, there exists some distance delta, and the constant Q, the number of bits you're going to read, and an explicit construction of locally testable codes. So error correcting codes with rate R, distance delta, and testable with Q queries. And in fact, relying on some prior work, you can get the trade-off between the rate and the distance to approach kind of the best known error correcting code. So it's like you don't even need to lose theoretically in the parameters at all, while you still get this local testability, which is kind of surprising. We thought that local testability requires much more redundancy, but somehow don't need that. So that's the main result. And very similar to our result, a recent result by Pantelev and Kalapchev came about that proves something very, very similar, similar or almost identical even construction. It's quite amazing. And they also get something called the quantum low density parity check code. But I won't talk about this aspect naturally. Okay, so let's see what the talk will be. By the way, so are we talking straight through? Do we have a break at some point? How is it?
It's up to you, I think, Irit. It depends also. How much time do you think it would be? 1.5 hour, or?
Second, another half hour, maybe.
Yeah, no. I mean, is it 1.5 hour or 1 hour, or what did you?
Yeah, something between. So I'll definitely end by in an hour from now. That was like the limit. We'll see, but okay.
So
we'll
it's up. I think it's up to you. If you feel like there is a good point of making a short break, then we can do it, I think.
Okay. All right. So here's the plan of the talk. Let's first talk about expander codes. These are specific error correcting codes that are from 1996. They're very, very beautiful construction. I want to go over them because they're somehow the basis of our codes. Then I'm going to define something that's like an expander graph, but it has a second dimension. This is an object called the left-right Cayley complex. It's basically a graph that also has these squares. Then I'm going to define the error correcting code on this Cayley complex. And then we kind of look at it, look at some properties of this thing, try to understand why it's locally testable. So this is in one slide, the definition of expander codes due to Sipser and Spielman from 96. So there's two ingredients. The first ingredient is a deregular expander graph. So by the way, when we say we construct the code, what we really mean is we construct an infinite family. And so here I'm thinking that we have an infinite family of expander graphs, number of vertices goes to infinity, but every vertex is only neighboring the other guys, and D stays fixed. So we have an infinite family of deregular graphs. And we also have one base code, which is a code on D bits. So D stays constant. It's just some subspace of 0, 1 to the D. And when I say here good, I just mean that it has sufficient rate and sufficient distance. We'll see in a minute. Okay, so by the way, expander graphs, maybe I forgot to say. So what are these? These are graphs that are on one hand very sparse and on the other hand very connected. So it means no matter how you split the vertices into two parts, there's going to be a large amount of edges crossing between them. So this is if you don't know what expander graphs. If you do know, then what we need here is that the second largest eigenvalue of this graph, of the matrix defining this graph, is smaller than the distance of this code. That's the requirement. That's it. Lambda smaller than delta 0. That's all. Okay, so I have these two components. How do I build a code from them, or how do Sipser and Spielman build a code from them? This is the code. So let's parse this. I have here a set of all functions that label the edges of the graph. So I'm thinking of all the bits are going to be labeling the edges of the graph with zeros and ones. And to define a linear subspace, I need to say what are the linear constraints. So for every vertex, I'm going to have some linear constraints. And what are they? They're going to say, look at the edges touching this vertex V. So these are D edges. And assume for every vertex, we numbered the edges arbitrarily. So then this, the F restricted to the edges of V is just a D bit string. I require that it's inside C naught. For example, if C naught was just the subspace that said all the strings need to be even, so the sum of the bits is 0, modulo 2, then all I'm testing is that for every vertex, the sum of the bits around this vertex is equal to 0 modulo 2. Okay, but if C naught has some other few constraints, then I'm checking a few constraints at every vertex. That's the definition of the code. Now, if you want to know, does this code have rate? Does this code have distance? So firstly, with regards to the rate, it turns out that if the dimension of C naught is strictly larger than D over 2, remember, this is a subspace in a D-dimensional space. If the dimension is strictly above D over 2, then just by counting constraints, you see that the dimension of this entire code is strictly larger than, so it's some positive dimension. This is just by counting. You have here n times d divided by 2 edges, so that's the number of degrees of freedom. And every vertex has some linear constraints, and you do the math and it comes out. So that's for the dimension. Now for the distance, it's more interesting. How do you use, what do you use to prove distance? So here you use the fact that this is an expander graph. To prove distance, you imagine you have some code word, and you want to show that every code word in this code actually has good large weight, has a large number of ones. And the way you do it is say, okay, suppose there's some non-zero edge. It's a non-zero code word. You have some non-zero edge. Look at one of the endpoints. This vertex sees this one here, so it sees some, on the edges touching it, it sees some code word in C naught. It cannot be the 0 code word because there's already one. So there must be a few other edges that also have ones, delta naught times D, other edges that have ones. So from a single coordinate that had a 1, you already deduce a few of them. But now you move to all of these neighbors. These are also vertices that see a non-zero. So they also have some more neighbors that have non-zeros, and you propagate. And the reason you're able to propagate is because of the expansion. If there was only a small number of vertices that are non-zero, and you just look at them, the expansion forces you to have many edges kind of coming out of this set. And there is some lemma called the Alon-Chang lemma that exactly allows you to deduce this. It's really like a very simple proof, very beautiful. Okay.
And it really comes out that the distance should be exactly bigger than the second eigenvalue.
Exactly, yeah, that's the Alon-Chang lemma, exactly. Yeah, it's really simple and beautiful. But okay, skipped it. Just to say, Sifter and Spillman didn't only prove this, which is already very beautiful. They also showed a decoding algorithm for this code. They showed that if you start with a word and it's promised to have only such and such number of errors, then some kind of iterative algorithm will find you the corrected code word. Okay, but that's outside the scope today. Okay. So now I'm tempted to say, look at this code. It has a lot of the properties that are like in a locally testable code. It has good rate and distance, we just discussed. And also, all of the constraints are what's called low density. Every constraint has size at most D, right? Because what is a constraint? Look at a vertex, you're looking at most at D bits around this vertex, and you're checking something. So it's very natural to say, okay, so here's my tester algorithm. Select a random vertex, look at the bits around it, and check if it's in C naught. Yeah, so of course, if that were the case, then I wouldn't be talking about it. So this is actually going back to your question, Alexander, which is, this is an example where it's not a good tester. So to figure this out, I need to tell you that actually the same code you could have defined, the Sipser-Spillman code, not by choosing the same C naught around every vertex, but for every vertex, you might choose a different C naught. It wouldn't change the argument as long as the distance locally is sufficiently large. So let's do this thought experiment where we start with some bunch of C naughts. And now for one vertex, we just remove one constraint from this C naught. So it's slightly bigger code, but maybe it still has enough distance. In this case, the code can grow by one. I removed one constraint, so potentially the code grew by 1 dimension more. If this is the case, and it doesn't have to be the case, but if all the constraints are linearly independent, it would be the case. Then I get now from the new code some words that are still far from everything else because there's distance all around. So it's a word that's very far from all the other words, but it only violates this one single constraint that I added. So that shows you why the naive tester is not, the naive tester which looks at a vertex, checks the edges around and tests, is not a good test. And there's a paper or a theorem by Ben-Sasson, Harsha, and Rashkodnikova that proves that actually there will be no test that will work for these codes. So that's kind of an answer to the question of showing a code that is not a locally testable code. All right, so I want to move towards defining the new codes. So just to tell you, one way to think about expander codes is that they're a kind of Tanner code. So Tanner codes, Tanner studied these things in the 1980s. And he defined the codes by looking at a bipartite graph like I have here. And he said, I'm going to put the bits on the big side, on the left side here. And I'm going to put constraints on the right side, but the constraints will be every constraint here. We look at a bunch of neighbors and require that these guys are in some C0. These are called Tanner codes. And the Sipser-Spielman code that I described in the previous slide is a instantiation of this scheme where the bipartite graph that you construct is derived from your expander by putting the vertices on one side and the edges on the other side. Okay, so this is also called the factor graph sometimes in coding theory. What are we going to do for the LTC? We're going to do the same kind of thing, but we're going to add another layer. So instead of having vertices and edges, we also have something of 1 dimension above, squares. You see here, these are the cycles of length 4 here are the squares. And now instead of putting the bits on the edges and the checks on the vertices, we're going to do a shift. We're going to put the bits on the squares.
Irit, sorry, can you repeat again the standard construction?
Sure. Yeah. Oops. Wrong direction. Yeah. Tanner said, I'm going to define a code based on 2 objects. One is some C0, like we had with Sipser and Spielman, and the other is a deregular bipartite graph. Not deregular, I meant that from the right, you have a deregular. The right-hand side is deregular, the left-hand side, I don't care. Okay, and how does Tanner define his code? He says, every right-hand vertex requires that the bits that he sees on his neighbors make a d-bit string. This should be in C0.
But it would be just one particular sequence, not okay. And this C0 is fixed for. It's the same for all the vertices, or
it's the same for all the vertices. I mean, if you can think of variations.
Okay.
But yeah. And Tanner also studied in his paper like specific constructions, like what if we take this bipartite graph to be the incidence graph of the projective plane, or he studied various specific instantiations of this. And the hope was to use these things to get better distance and to prove a decoding. And it was really a generalization of codes from the 60s studied by Gallagher. Gallagher studied the same type of thing, but where the constraints were always just XOR. Every constraint on the right just required that the XOR of all the bits it touches is 0. That's kind of the Gallagher codes. And he studied it for random bipartite graphs. These are called the Gallagher LDPC codes. And Gallagher proved that they have distance, and he showed it, an algorithm for decoding. So Tanner generalized it, and he said every vertex doesn't need to just XOR. You can actually check membership in some small code. These are Tanner codes. And the codes I described in the previous slide are just a specific instantiation of this. So we're gonna now push it one level up and say, oops, No, I'm going the wrong direction. Push now, add a third layer, the squares, and instead of putting the bits here, we're going to put the bits on the squares. Okay, so pictorially, I'm putting a bit on every square. And now my constraints are going to be on the edges. So every edge will look at all the squares touching it and require some linear constraint. And why is this good? Because now the vertices give me kind of dependencies among the constraints, which is useful because, as maybe we saw in the earlier example, if the constraints are all linearly independent, then this gives rise to some counterexamples. You kind of need the constraints to be dependent on each other. And this is tricky, right? Because the constraints are small, they're a constant size. So how will you get dependencies between constant size vectors without kind of making them grow? Well, okay, but kind of this is where this geometry or combinatorics of the graph helps us to construct such things.
And by squares, you mean just 4 cycles? Or...
Yeah, so we'll see. I'll now define it.
Okay.
Exactly. So far, it was just kind of schematic. Okay, so now I want to define this object, this left-right Cayley complex. It's not a complicated object, and from this, we will know what the squares are. So now we're moving to a slightly more algebraic situation. We have a group G, finite group, and let's recall what is the Cayley graph. So if we have some set of elements of G that if A is in the set and also A inverse is in the set, then I can define the Cayley graph with respect to the group and with respect to A. It's just a graph that has vertices, a vertex for every group element, and an edge moves you from G to A times G. And this is an undirected graph because from A times G, you can move to A inverse times A times G, which is G. So it's just a graph. Okay. Now what we're going to do is we're going to take two sets, A and B. They can actually even be the same set, but let's just think of them as two separate sets, A and B. And we're going to look at the two Cayley graphs, one with respect to A and one with respect to B. But with a slight twist. The twist is that the A edges are going to be with left multiplication. So you move from G to A times G. And the B edges will be with right multiplication. You move from G to G times B. Okay, so it's almost the same, but slightly, this is the slight twist. That's why we call it a left-right Cayley graph or complex, because we have this right multiplication and left multiplication. And so in the picture, I have these as blue edges and red edges. And you can already see here that this causes these cycles to close, right? Because if you move from G, you can first do left multiplication, then right, or you can do it vice versa. And this will give us the squares. So I'm going to now define it. Okay, so fix some group element G and fix two generators, one in A and one in B. So I'm going to define for the triple AGB, I'm going to define a rooted square. What is this? It's this cycle. The root is G. You go from G to A times G or to G times B. But then if you walked on the B, your next step will be to walk on the A. So you move from GB to AGB. And if you were here, from AG, you walk to AGB. So you get this square for every triple, A and G and B. And you notice that every square you can look at it from 4 different points of view. So this square, you can think of it as AGB, but you can also think of it centered around GB. And then from GB, you move to A times GB, or to B inverse times, to GB times B inverse. So that would correspond to this triple. Okay, so we're gonna define an unrooted square to be the equivalence class of all these 4 things. So the 4 rooted squares together make up this equivalence class. So that's our formal definition of a square. Okay, so you see that the square naturally contains all these 4 edges. It's kind of easy to see who are the edges that touch the square. and who are the vertices that touch the square. So it's kind of clear from the picture. And we'll denote, so really what we are looking at is a graph. It's the union of these two graphs, the left graph and the right graph. And on top of it, we have this two-dimensional thing. These are the squares, and we define them to be the set of triples modulo these equivalence class relations. Okay, so that's the combinatorial object. Okay. So I guess this is a recap. We have a group, we have two sets of generators, symmetric sets, meaning they're close to inverses, and we define the left-right complex to be the following complex. You have vertices G, you have edges that go from the left with A and from the right with B, and you have the squares. And we're going to say that this complex is a lambda expander if each one of the graphs of the Cayley graphs is itself a lambda expander. And we know that there are infinite families of bounded degree expanders, so you also get that you get explicit constructions of lambda Cayley complexes like this. So now what's interesting, kind of nice, is to look
Irit, and is it important for us to remember what is a lambda expander or not really? Like what does lambda stand for?
Okay, it's not so important, but since you asked, let's say it anyway. So as I said, an expander graph, it's really important to understand that it's a graph that's kind of well connected. Even though every vertex has only a few neighbors, somehow when you try to separate a set of vertices, you cannot do it. Take a set of vertices, there's many edges going out. That's conceptually. And technically, a good proxy for this is to look at the second largest eigenvalue, and that's when I say a lambda expander, I mean that the second largest eigenvalue normalized is bounded by lambda. Okay, so what's kind of nice is to look at neighborhoods inside this object. Okay, so let's look at that. So suppose I have an edge from G to A times G. Okay, and now I'm trying to figure out who are the squares that touch this edge. So for every element B, for example, B1, I have a square that goes from G to B1, and also from AG to AG B1. And these two are also connected by an A, but by the same A that was connecting me here. So from GB1, I go to AGB1. So I get this first page, and you see here, it's like a book with a few pages. So the edge from G to AG is like the spine of the book, and I have a few pages. And the pages are naturally identified with the different elements of B, right? If I now move to B2, then I have this square from AG to AGB2 to GB2 back to G. So the pages of an A edge are naturally identified with B. And symmetrically the other way around. If I have a B edge from G to GB, then for every element A, I have a square. I go from G to A1G to A1GB, back to GB, back to G. So I have these squares. So it's like a book where you can open the pages on all sides, you know, like there's not only one spine, but every part of the page is a spine, and you can move like that. Now let's look at the neighborhood of a vertex. It's a bit more complicated to draw. Okay, so I have a vertex G. Here it is. And this guy, if you think of just the graph, then it's simpler. It has, you know, some A neighbors and some B neighbors. So here I drew them, like one is in the blue color and one is in the red color. On the left, I have one kind of neighbors, and on the right, the other kind of neighbors. Now, for every choice of neighbor from here and neighbor from here, there's going to be a square closing this choice. Okay. So for every choice of A from here and B from here, there's going to be one square. This edge is like a spine, and these are the pages along this spine. And this edge is like a spine, and these are the edges along this spine. So, okay, it requires some staring at it, But the thing to take away from this is that if you fix G and you vary the different A's and B's, what you get is like a table of A cross B different squares. For every choice of A and B, you have a square. And if you look at the kind of the green grid, it's supposed to give you like a map of this tableau, this A times B tableau. Okay, and there's a question whether it's a bijection or not. It's a technical matter. If you assume something about the generators of these groups, then you get that it's a bijection, but it's not important. So you see, you have this picture, you know, sometimes there's these decorations where you fold from this side, you fold from that side. So it's supposed to be a picture. This is thanks to the Simons Institute. They have a really awesome graphics designer who did this for us. Okay. Okay, so we finished describing the left-right complex. It's kind of a cute thing. Now I want to define the code. Okay, so it's very similar to the expander code. We start with this complex, and we're going to fix a base code like we fixed in the Sipser-Spielman case. But now we have A and B. If you want, you can think of A equals B, and then you only need to fix one base code. Otherwise, you can fix two different ones because maybe B and A don't have the same size. So you fix two base codes. And now, how do you define the code? So we said that the bits are going to be on the squares. So it's a collection of functions on the squares. And we said that every edge will impose some kind of constraints. Basically, remember that if we were an A edge, then it's like a spine and the squares are like pages in a book. And the squares are naturally identified with the elements of B. So it's natural to view the bits around the edge as a function from B to 0, 1, essentially as a string in this, in 0, 1 to the B. So the constraint will be, okay, I want this string to not only be just a string, it needs to belong to CB. That will be my constraint. And if it's a B edge, the book around it is like, the pages are like in A, you want this string to be in CA. So this is a definition formally. It's the set of all functions from the squares to 0, 1, such that for every triple AGB, okay, what is this notation? G is the vertex. GB, you think of it as the edge from G to GB. And dot means you look at all the, you plug in all the different values of A, you get all the possible squares touching GB. You want this to be inside CA. And the same thing for the other guy. So that's the formal definition of the code. And that's it. Okay. So now I'll tell you a few properties of the code. First, I want to say rate and distance. This is exactly like in the case of Sipser-Spielman. How do I show that the rate is positive? Well, it's not necessarily positive, only if the rates of the local codes CA and CB were sufficiently large. This is just what happened with the Sipser-Spielman code. I wanted the dimension of the local code to be above D over 2. And then when I count how many degrees of freedom versus how many constraints, it works out. So the same thing happens here. It's just a one-line thing, but I'm not going to bore you with it, but it's really just a simple counting. Okay, what about distance? Also similar to what happened with Sipser and Spielman, you can start with some code word that's not the 0 code word. So there is some square that's not 0. And then you notice that along each one of the edges touching the square, the book must be a non-zero code word. So there's many neighbors of this square that are also non-zero. So you move to one of them. And then you move to another edge, take it as the spine, and you move more. And thanks to the expansion, this will propagate. And again, you see this delta naught minus lambda. It's the same expression that relies on the Alon-Chang lemma.
Wait, sorry, what is delta 0 here?
Delta naught and R naught are the parameters of the base codes, CA and CB.
Okay.
But, yeah, I didn't write it. sorry. I'm just thinking that these codes have distance at least delta naught and rate at least R naught. And notice that for this to be positive, you need R naught to be at least 3/4, so a bit large. Okay, but also notice, interesting, if you think of R naught as kind of a 1 minus epsilon for small epsilon, then also this expression is 1 minus 4 epsilon. So it's like if you start with codes that have very high rate, you'll end up with a code that has very high rate. Okay.
And what is the total, like, how should we think the total dimension of the thing? Like, is it so ND squared, something like that?
Great, thanks. So how many squares do we have? I forgot to count. So how many triple, so a square is a triple from G, A, and B, right? So G is like my N, number of vertices. And then if A and B have size D, then it's ND squared. But of course, it's like when edges, you need to divide by 2 because you can count them from both endpoints. So here you need to divide by 4 because we've counted rooted squares. We divide by 4, we get ND squared by 4. That's like the length of the code word. Okay.
But still there is some decrease in the rate and in distance. So if we start from a code on the boundary of Gilbert-Warshamov, then we are no more on the boundary, yeah?
Absolutely, we lose. This is already not the Gilbert-Warshamov trade-off, because here we have 1 minus 4 epsilon, and this is already delta to the 3. Even if lambda is tiny, this is delta to the 3. It should have been delta. So this is not the Gilbert-Warshamov trade-off. But here I'm just going to apply some work by I'm not going to remember now the name. I have it written later. That said, it's really incredible. They said if you have a locally testable code with rate going to 1, rate being close to 1 as much as you want, and this can go to 1, then they did some transformation that makes it with the Gilbert-Warshamov trade-off and still locally testable. And actually, if you look at their paper, they viewed it as a potential way to prove impossibility for LTC. They said, if you manage to prove an LTC, it will prove an LTC with Gilbert-Warshamov parameters. That's clearly impossible. So, of course, they allowed both cases because people really didn't know, but it just seemed quite surprising. Anyway, by the way, I have to say that kind of humblingly, all this sounds very good, but if you try to implement these codes and think, oh, wow, I get codes with such great parameters. To get these parameters, you need the block length to be so huge, as far as I know for now, that it's only theoretically possible. In like normal block lengths, if you want your block length to be reasonable, this is far from getting good parameters.
And what it makes so high? So the construction of the group when A and B should be difficult, or what? What is the obstacle here?
Okay, first of all, even to construct just plain expander codes, you need an expander graph, which actually we have wonderful number theoretic constructions, very efficient. With that's actually there's no bottleneck. Whatever you believe you should get, they actually give you. But now you need to also construct a code that has delta naught meeting lambda. And somehow, like when we did the calculation quickly, we got a block length that's around 1,000 bits. So not smaller than that, even just for expander codes. Here, you have some more requirements that come from local testability, so it makes it even bigger. Okay, but of course, maybe it's just a starting point and there's room for, I'm optimistic, maybe we can make it better, I don't know. That's kind of things people in theory usually don't think about, which is, okay, but what's the minimal N0 where this is actually meaningful? Okay. All right, so let me talk. Okay, so what did we do so far? We described this complex and we defined the code. But I want to now tell you another feature of this code, and we said that it has rate and distance. I'm going to talk about local testability. So for that, what I want to do is look at local views on this code. Meaning, we already said that if you look at an edge, the squares around it will belong to the base code. This was by design. Now I want to say or study what happens if I look at a vertex and I study all the squares that touch this vertex. Remember, we had this kind of crazy picture with the grid. So we're going to get to that. Okay, so this is the local views. Okay, so here is my claim. Suppose I fix some code word, some function from the squares to 0, 1 that is in the code. Okay, and now I want to look how the bits of this function look like around a specific vertex G. Okay, and here on the bottom I copied the definition of the code. So, you know, for every fixed G and for every A and B, I have these requirements. So remember that the squares touching G can be arranged in a little table, A times B table. And every entry here in this table is one of the squares. So I can copy the bits of F to the entries here. The bit corresponding to AGB will be in location AB. Okay, so now what does this claim say? It says if you do that and you look at this table, it will have the following property. It will be in the code that's called CA tensor CB. Just to parse what this means, it just means these are all the tables of size A times B, such that every column is in CA and every row is in CB. This is just the definition of this. We call it a tensor code. It's the tensor of CA and CB. Okay, so what is the claim saying? The claim is saying if you copy the bits of F2 around G to this table, you will see this behavior. Why is that? Okay, let's fix some B. Okay, so it means I'm fixing some column. So I'm looking at all the squares that touch the edge GB. Okay, so you fix this edge from G to GB and you look at all the book around this. Okay, and by design, these collection of squares belong to CA. This is what it means to be in the code. This exactly corresponds to having this column in CA. And symmetrically for fixing a row and looking at all the squares touching the edge AG, from G to AG, and this will be in the other code, CB. So indeed, your local view is a tensor code. Now, what's kind of special about tensor codes? Tensor codes have some redundancy among their constraints. If you look at what are the linear constraints that define a tensor code. So in every row, you need to be in CA. In CB. In every column, you need to be in CA. So if you count the constraints and you do the math, you'll see that there's more constraints than dimension of the dual code. There's some redundancy among the constraints. Okay, because some constraints are counted twice, like tensor of a constraint from CB and a constraint from CA is a constraint, and it appears both in the row constraints and in the column constraints. Okay, I don't know if I made a lot of sense. Just to tell you, there is some redundancy and that's helpful. And so this is the theorem we prove. We prove that if you take this Cayley complex with a group and two generator sets that make an expander, and if there is some condition on the tensor code, so the fact that a tensor has redundancy, it's always true, but we need an additional property called the robust testability. So it's some property about the tensor code. Okay, so if you have this property and you see that it also causes you some kind of constraint here between lambda and delta naught and this parameter rho. But anyway, if this happens, then your entire code is locally testable. And the tester is what you would expect. It's basically select a random vertex, look at the entire table around this vertex, A times B, and check that whatever you see is inside this tensor code. Okay, so that's the tester. Okay. And then this is what the theorem says. It says, for any function f, I don't ask for it to be in the code or nothing, the fraction of local views that are not don't look like a tensor. So I'm going over all the vertices G. I'm looking at the local view at G. This is a little table A by B. And I'm asking if it's in the tensor or not. And I'm counting which fraction of vertices are not happy. So this fraction is lower bounded by the distance of F from the code. Okay, so it can't be that you kind of, this code doesn't have the situation where you have a word that's very far, but somehow it fools all the constraints except for one or two. Like we did have with the expander code. In the expander code, we said, you know, just change one constraint. Now you'll get a new code word that you didn't have before. And this one will be very far, but it only violates this one constraint. Here, this cannot happen. If you want to think about why, you will see that if I change one constraint, like I remove one constraint, the redundancy will force this constraint to happen anyway. So I can't really, if I remove a constraint, nothing happened, the code stayed the same. And somehow you need to, what the theorem says really is that you need to change a lot of constraints in order to get a code word that's far. Okay, I guess now it's a question of do we need a 5-minute break or should we, what do you think? I don't have too much more.
You can explain informally. So finally you have, again, if you look at your picture, you have vertices and you have the squares.
Okay.
And also you have a kind of a graph of bounded degree. For every vertex, you check that the set of all squares connected to this vertex has some, belongs to some code.
Right.
So again, you are in the same model. You have a graph and you have a code. But still,
like in the you mean it's like a Tanner, it's a Tanner graph.
Yeah.
It's a Tanner code, yes.
Yeah, but still, it's probably the idea that this graph or this code have some special properties which guarantee nice behavior of the entire construction, which was not guaranteed if there were only expander codes.
Right.
So what are the specific properties in this graph and in this code which are achieved by this nice, strange thing?
Right. Okay. Thanks. So we had this Tanner code, which basically I had a bunch of vertices here where I put the bits, and I had a bunch of vertices here where I put the constraints. And every constraint here looked at D neighbors. So there were D neighbors. And it looked at all these bits, and it says this needs to belong to some C naught. This is the kind of the Tanner scheme. And we had one, so now we have two instantiations of this. One, so maybe I copy it twice. So one time where I put here, so what is this bipartite graph? One time I put here the edges of some other graph G, and here I put the vertices of G. And I connect a vertex V is connected to all the edges that touch V, right? To E1, E2, ED. V is connected to all the edges that touch it, and that gave me the Sipser-Spielmann code. What we call expander codes. And the code that I'm talking about today is almost the same, except here I put, for this bipartite graph, I put the bits on the squares. Okay, so I guess every bit here was an edge. Every vertex here was a vertex. Maybe I change color. Now I move to green. So, but now, I'm going to have every vertex here is going to be a square. So these are going to be the squares. And the vertices here are going to be the edges. Every vertex here is going to be an edge. This is like a GB or an AG. And this is like an AGB. over here. And I connect, a GB edge is connected to all the A different edges, and an AG edge is connected to all the B different squares. Right, so this is the squares code.
But still, you can also, if you look at your final local tests, they are also of the tenor form. You have an
Exactly,
additional layer.
And the tests are select, right? Even, you know what? If you want, okay, you're right, absolutely right. In fact, I'm not going to, that's one way to describe it, but there's another way to describe it. Okay, duplicate it one more time. Use the fact that I have this technology, right? So let's move here. So our code, you can also describe it in a third way, which is, now instead of edges here, I'm going to put the vertices here. Okay, so now I'm not going to have, I'm going to have here a vertex. But now this is not D anymore, it's going to be D squared. Every vertex touches D squared different edges. And this vertex, the C naught that we're going to choose is the tensor code itself, right? That's what you were thinking?
Yeah, the tensor code. So again, you have some code and some graph, and
right.
some
so
properties of the code and the graph guarantee that it behaves well. Because
right,
now the testing is just like what failed before, just taking a random condition and try it. And
exactly.
Now this.
Exactly. So whereas here, so now what is my test? The test is, you know, out of all of these possible vertices, okay, make it bigger. All these possible vertices, choose one at random, look at the D squared neighbors that it has, check that they're in the tensor code. If no, say no. If yes, say yes. That's the test. Previously in the Sipser-Spielman, we had the same thing and we suggested, okay, let's look and see if the test works. Select a random vertex, look at its neighbors, read this, and so on. And we said that here it fails. And I told you that there's a paper by Ben Sasson, Harsha, and Rashkodnikova that showed this, and so on. So what's the difference? The difference is in the linear, well, one difference is in the linear dependency between the constraints. In the BHR paper that shows no LTC, they show it in the condition that all the linear constraints here are all linearly independent. So kind of, if you look at all the constraints, they're full rank. There's no linear dependency among them at all. Whereas here, we know that there's a lot of dependency in our code because, you know, this vertex checks constraints around all of the edges that touch it, but other vertices also check those constraints because they also look at these edges. And also there's more dependency because tensor codes themselves have some redundancy. So like, first thing I can say is that these linear constraints are certainly not independent. That in itself is not a proof. And I don't know very good conditions to tell you, if your constraints look like this, you're LTC, and if they look like that, they're not LTC. It's a good thing to wonder about. Okay, as long as I already have this on, maybe someone wants to ask other questions. Okay, so let me finish. Let me do a little bit more analysis here. Okay. Okay, so I want to show to you something about why this is locally testable. Okay, and to show that it's locally testable, you essentially also show a kind of algorithm, as I said. So we'll see this. Oops, sorry. Okay, so how do I prove that something is locally testable? I start with some function, some string. Okay, f is a string that labels the squares, and I measure how many, what is the probability of the test rejecting. So this is really the fraction of vertices that around them, they see something wrong. So what I want to do is, if this is, I pretend, imagine kind of in my head that this is small. And I say, if it's small, I'm going to find a code word. F prime is actually in the code that's close. That its distance is proportional to this. So we do it with this algorithm. So let's look at this algorithm. So first step, kind of initialization. Every vertex looks around it at its little table, and it sees if it's happy or not happy. If it's happy, meaning what it sees is already a little tensor code word, then that's fine. If it's not happy, it sees something that's not a tensor code word, then it finds a tensor code word that's closest possible to the local view. So maybe there's more than one, you break ties arbitrarily. But now every vertex, at least locally, corrected, it did this local correction of making itself happy. Okay, so at this point, if the code word was perfect to begin with, then it's still perfect and we're happy. It could be that maybe one bit was off, and now just by these local corrections, all the vertices corrected this, that even know about this bit, corrected it in the same way, and now everyone is harmonious and there's no disagreement, and we're happy also. But it could be that one vertex G corrected some of its bits one way, but a neighboring vertex G corrected the same bits in a different way. And the different local views are now disputing. They're in conflict. It could be. So we're going to measure this. Phi is going to be the number of edges of pairs of vertices that have an edge between them that disagree with each other. The local view here disagrees with the local view there.
So it's weighted how many, if it's half, then it's more than it's one versus all, or each edge can be disputed between only two vertices.
Yeah, so to say it again, every vertex holds its own local view, and two neighboring vertices are either in agreement or they are in disagreement.
Right. It's just
how many pairs disagree. And this is kind of my
correction in terms of code CA and CB separately. What we do is just CA tensor CB code, yeah?
Yeah. I mean, in this analysis, maybe there is a way to do it separately. I don't know. Okay, so we have this bunch of disputing edges. Now, what we do is kind of a local correction. A vertex G looks at all of its neighbors. It has A plus G different vertices that are neighboring, and it sees what these guys think. And maybe there's a better local view for this G that will make it agree with more of its neighbors. If that's the case, then G will change its value. And what will happen when G changes its value? The number of disputed edges decreased. So we can keep going like this, and phi will just reduce and reduce until we're stuck, and there's no more such moves that will cause phi to decrease. And when we're stuck, that's it. We have two cases. Either we're stuck because there's no more disagreement, everyone is in harmony. That means we found a good word. Or else we're stuck, but there's still some problems, but there's no local change that will make it better. So, okay.
And when we say change TG, it's not, you're not necessarily changing it to another TG that is also closest to F, right? It's to any
right,
TG.
Exactly. But at this point, after the initialization stage, we throw F away. We don't know about it anymore. We only kind of care about what the neighbors think. We kind of adapt the local view according to the neighbors. Okay, so now I want to observe firstly that if I know that I start with a function f that had relatively few local views that reject, then actually the number of disputed edges will also not be too large, because if both endpoints of an edge didn't reject, they were happy, they looked at a perfect picture, then they won't be in dispute, right? Because they both agree with F, so they also agree with each other. So the only case where a disputed edge happens is if at least one of the two, maybe both, disagrees with F somewhere. So if I know that there's only a little bit of disagreement, there's going to only be a little bit of disputed edges to begin with. And now I do this algorithm and I reduce it even further. Okay. So how do we analyze this? Firstly, you see that the number of steps is bounded by, at every step you reduce phi, so the number of steps is smaller than phi, which is roughly the rejection. If phi ends up being 0, then we've actually proven, this was the inequality we wanted to prove. It's copied from here. The reason is that at every time whenever we decrease phi, we change f until we end up with f prime, but the number of changes is proportional to phi. So it works out that really the amount of changes we made is proportional to the rejection. And the difficult thing to prove, but I won't have time for it now, is to show that actually, if you ended up with 0, that means you're close to a code word, and this f prime is a close code word. But if you got stuck without getting to 0, it means that actually you had to be very large to begin with. Okay, so basically there's no local minimum that's small. All the local minimums are either large or 0.
Sorry, 1/10 is 1/10 of what?
Okay, thanks. Oops, sorry about skipping here. Right, the normalization, sorry, the fraction of edges. So if here I said that phi is a number, and here I'm saying 1/10. Sorry.
Among all edges.
Say again?
Among all edges.
Among all edges. I'm saying here, if phi is large, it has to be like 1/10 of the total number of edges. That's what I meant, sorry.
And this is some kind of, well, expansion or high dimensional expansion, or?
Right, yeah, so okay, so I'm going to skip it. There's some argument here. Sorry, I was skipping. There's some argument here, and I'm not going to go through it, just to say that there's some propagation. It's like in the distance argument, but here you also need a 2-dimensional propagation. It's another random walk that goes from edge to square to another edge, something like that. But basically, it's the same idea of just propagating on an expander. Okay, so to conclude, I have this slide about high-dimensional expansion. As I told you in the beginning, it's kind of an idea that it should be relevant for LTCs, trying to do it in different ways. The reason is that these objects have this local to global thing. Here in this construction, you saw that tensor codes have this local redundancy, and this kind of translated into this global redundancy. And this dates back to Garland, who used this kind of property for showing something completely different about the cohomology of quotients of affine buildings. Okay, actually, this was our direction. We were hoping to construct these codes using these quotients. There are these beautiful quotients constructed by Lubotsky, Samuels, and Vishna. But we didn't, we have these conjectured things, but we couldn't prove it, and we ended up doing it this way. Okay, and I guess kind of the two questions that I'm really interested in, can you construct probabilistically checkable proofs with some similar ideas? And also whether this can be practical in any way, like actually use this to encode things. Okay, I guess that's.
And for the first question, is there some result that if we can reach some unbelievably good things about local testing, then we will just imply PCP without using the construction, but just using the code?
Yeah, no, excellent question. It used to be that people believed it because all the time we would get better LTCs and that would imply PCPs, but really there is no such formal theorem, and actually we don't know how to do it. So, yeah.
Great, wonderful talk, Irit. Very interesting. Any questions?
Yeah, I would like to ask another question about the same graph that Alexander was asking about a bipartite graph when on the left we have squares and on the right we have edges. You just mentioned a random walk on this graph. Does it mean that if we just look at this graph separately, then it also has a good second eigenvalue?
Ah, you mean the graph from square from, yeah, I guess let me move to this.
From square to vertices.
From squares to edges.
Yeah, so there are several different walks you can consider. So now I'm talking about like high dimensional random walks, for example, from edge to square to edge, right? Something like that.
Yes.
Of course, so not all of them have good second eigenvalue. For example, if I allow myself to walk from an edge to some random square that touches this edge, and then when I'm on the square, I can choose any one of these 4 edges randomly, then there's some probability of actually a half that if I was starting from this edge, I'll go to this edge, which also touches this vertex. So if you look at the set of all squares that touch this vertex, it's a set that you can only exit it with probability half. If you start from this edge, either if you go here or here, then you exit, but if you go here or here, you don't exit. So you have these local obstructions of like staying around a vertex that you need to take account for. And once you take account for them, then you have very good expansion. So for example, a random walk that's a good one is like what we call the parallel walk. Here, the parallel walk says you start from an edge, you must go to the parallel edge. You cannot go to this one or this one. Okay, so this will actually be, this walk is expanding. You move around the graph. You get to a large chunk of the graph, but not to all of the graph, because the label on your, in our case, if the edge was like from G to AG, the label here is A, then also here it's from GB to AGB. So the label here is also A, the kind of the generator that makes this edge. So if you use the parallel walk, your label is always going to be A, but you'll get to all of the A edges, which is a constant fraction of the edges of the graph. So there are different random walks here and you need to analyze them carefully. But basically what's going on here is that to understand these kinds of random walks, you look at the obstacles that can be, for example, all squares touching a vertex. And after you've finished understanding them, everything else kind of expands, okay.
But this parallel walk is just a walk in B graph, no?
It's exactly a walk in the B graph.
Yeah.
That's right. That's exactly right.
Same property that we want.
Right. So you use the expansion of the B graph to show that this is a very good expander. You have here like different components. Each one of them is isomorphic to the B graph. Does this make sense? Is this what you were asking? Or?
Yeah. Thank you. Just another question, so rather a request, not a question. You skipped lots of pages in your presentation at the very end. Could you put it somewhere just for meditations of people from the talk? I think it could be interesting.
Sure, thanks. I'll do it. Actually, I was planning to do it for a while. I'll put it on my webpage. Hopefully tomorrow it will be there.
Thank you.
Yeah, you can also, if you want it, you can send me the link, or I can just then put it to the webpage or somewhere for the seminar so that people can find. Yeah.
Anyway, the pages are on the recording. They are just very fast.
You can pause.
Thank you.
That's true. Yeah.
Yeah. Any other questions?
Sorry, this code is used on graphs. I'm wondering about other settings. For example, hypergraph. It means we have the vertices is the same, but it's we have more than 2 vertices, at least 3 vertices. Or other setting, for example, super graph, we have a lot of vertices in one super vertex. Or super hyper graph, we have more than 2 connection between super vertices, 3 at least. Is it possible to bring these ideas in these settings, or is it studied to use code by modeling with these settings instead of a graph? For example, we have more than 3 codes in the one edge. It's called hyper edge or something like that.
Yeah, so certainly. So the question, if I understand the question correctly, what about like hypergraphs? Where kind of a hyper edge has, I don't know, five vertices, and you have this kind of situation maybe. Certainly, it's very interesting to come up with codes on any type of object, combinatorial object. What I kind of zoomed through very fast was these high-dimensional expanders. These can be viewed as hypergraphs instead of graphs, where, for example, a 2-dimensional expander, you have vertices, edges, and also hyper edges of size 3. We call them triangles sometimes. And the difference between a hypergraph and a simplicial complex is just that in a simplicial complex, when you have a hyper edge, you also have all the possible subsets as hyper edges, but otherwise it's the same. We tried to, as I said it very quickly, we did try to use kind of very special constructions of hypergraphs that come from number theory. You take what's called the Brotitz building and you look at the quotients by arithmetic groups. But so far this didn't work for us. It's a good thing to study.
Thank you.
So far, this is the only construction of such codes, right? Because you said there was this essentially same construction from 2
the construction
professors.
Of Pantelov and Kalachev. I forgot to mention it here. Let me take another minute to say. The way you can view this square complex is you take the Cayley graph of G and A, and you take the Cartesian product, just a graph product, with the Cayley graph of G and B. So it's like you put the one Cayley graph here in the horizontal axis, and one Cayley graph here in the vertical axis. And then, the edges here are the edges of this graph, and the edges here are the edges of this graph. And then you naturally have these squares. Any Cartesian product will have squares. But the way this construction works is that when you do the Cartesian product, the number of vertices you will have is a square. It's G squared. But now you divide by G. You basically identify pairs G1, G2 if they have the same product. So you get a linear construction back. And this is more the way they were looking at it, not even like this. They look at it as some kind of homological chains and product of these chains. But actually, when you look at the details, it's a different viewpoint, but it's the same construction. It's kind of crazy, yeah.
Yeah, interesting. And no other construction, right?
As of yet.
Yeah, as of yet.
Yeah. Earlier constructions with a rate that goes to 0, kind of the most famous construction is just the Hadamard code. It's a locally testable code. The rate is logarithmic. It's a well-loved code.
Yeah, great. No, that's very interesting. Any other questions? Well, if not, well, thanks a lot, Irit. It was a very pleasant talk.
Thank you. Thanks for all the
things.
questions. It was very nice.
Yeah, thanks a lot.
Okay, thank you. Bye. Nice to meet some of you.
Yeah. Bye, Irit.